Right, welcome to video 6 in probability functions. This is on hypothesis testing with normal distribution, with a normal distribution. This topic is often portrayed as being something really awful and beastly, but in actual fact, it's not really as bad as it's portrayed. And if you understand the normal distribution and how to use the normal distribution, then really all it's doing is applying a little bit of structure as to how we apply it. So really it's nothing to be feared. Okay, so let's just go straight in, have a look. School children entering a sweet shop spend a mean of £1.50 per visit with a standard deviation of 36 pence. The shopkeeper puts all the prices up. The next 100 children spend on average £1.45. Has the price rise caused sales to drop? We've done this before. Obviously, we've just done this in the previous video. Assuming you will have seen the previous video on the normal distribution, and what we calculated basically is that the probability of getting an average of £1.45 is this fairly low figure, and so is that very unlikely? Is it enough for us to actually say, yeah, price rise has caused sales to drop? Well, that was the conclusion that we ended up with in the previous video. But I mean, the point is that sufficiently unlikely for us to want to change our assumptions as to what the mean is. Really, we have to take a judgment here based on what we're looking at and what the consequences are. First of all, how much evidence is there for the null hypothesis anyway in the first place? I mean, is it something that's really been established for a long time, and there are lots of things that actually are based on that assumption? What's the risk of changing assumptions of our parameters? In other words, and the other thing is, what's the risk of not changing any assumptions about our parameters? So what we need to do is we need to set some thresholds and set some rules, do the test, and then if it passes the threshold, we draw one conclusion: either the original assumptions were not good and we're going to change them, or the other way around. So we have what we might call the hypothesis testing process. And just to go through the main steps of this, first of all, we need to identify the underlying probability distribution. Obviously, in this section, we're talking about the normal distribution, but we may be using other ones, and we will be doing the binomial distribution as well. But essentially, there's all sorts of distributions that we may be using. We define the null and alternative hypotheses. Well, the null hypothesis is basically usually this time-honored assumption about a parameter. In the case of the normal distribution, it's very often the mean. Nearly always the mean in terms of the questions that we'll see at this level. And the alternative hypothesis is more or less, well, not the null hypothesis, but there are a couple of different options with that, which we will get to. Define the significance level of the test. Right, okay, so what we're sort of saying with the significance level is depending on how serious it is and other factors. How low a percentage do we have to get here in this probability statement? Well, we're looking at how probable is a test statistic less than what we get for it to be significant. We might choose 5%, we might choose 1%. If we're choosing a very low significance level, what we're actually saying is We're not really. We're only going to abandon our original assumptions if there is some data which is really, really compelling. So that's the basic idea of the significance level. We express the significance level in terms of a percentage, and in our distribution, in the graph of our distribution, then it would represent some, the tail or tails right at the end of the distribution. So we'll see more about that in a moment. Then we take the data and calculate what we call the test statistic. Well, the test statistic in the case of this shopkeeper thing, that would be that our 145 pence there. And this is a sort of important part of, part of the process, in the sense that we should do all this stuff first before we then take the data, because the thinking is basically, if you take the data first and then you start to form your hypotheses are influenced by your data and not by the what you're trying to prove or disprove. And then we're going to compare the test statistic with the significance level. We'll come to that because as those things stand, those are usually not directly comparable, so we have to do a little bit of work on that. And then we draw conclusions as to whether or not we stick with the original parameters or whether we take steps to change it. Right, okay, so let's just have a look at a little bit more detail about what we're talking about here. So what we're saying is, if a test statistic could have arisen by chance under the distribution implied by the null hypothesis, then the parameters we regard as still being possible. So if we imagine this is the distribution, and this is what we're assuming under the null hypothesis. Yeah. So if we're thinking about the mean, which is the parameter we kind of most often think about, although it's not necessarily what we're thinking about. But so if this is the distribution, therefore the mean, normal distribution, obviously, this is the mean under the null hypothesis. In other words, our sort of baseline assumption is that the mean is this, and by definition, therefore, it is the sort of center of this distribution. Then, if we define our threshold level, we talk about the alpha level. That is this value here. Now, this might be 5%. Well, what does that mean by 5%? Well, it means that 5% of the probability density area is in this tail to the right, and then 95% down the rest, obviously. So this also is identifying the critical value. Now, the alpha level is a percentage. The critical value is a number. Okay, and therefore we're saying the critical region, the region in which we started to think, right, well, this is a bit unlikely, falls to the right of here. So basically, what happens is if when we take our test statistic, we find that our test statistic falls in this critical region, then what we're saying is, well, that's pretty unlikely, in terms of our test. So if it's so unlikely, then we're disinclined to think that this is actually the mean. And maybe the distribution, if it is a normal distribution, maybe the mean is further to the right than that. Okay, so that's the idea. And then, conversely, of course, if the test statistic falls in this area here, then we go, well, it could just be random variation. Any observation that we take from this normal distribution could doesn't have to be on the mean, does it? It can be anywhere up and down here. So that is the kind of the idea. Now, as I said, the test statistic and the alpha value are like different currencies, percentages and values. So what we need to do is, well, first of all, just understand this table is that when we're talking about the distribution, the baseline distribution under the null hypothesis, the probability is the alpha level is a probability. The critical value is a value. We derive a test statistic. Okay. And the level at which the test statistic falls defines the p-value. So the p-value would be this area to the right here. So we can compare probabilities or values. So, you know, we can match that against that. We could say, well, if this p-value is smaller than the alpha value, then we reject the null hypothesis and you know, the prevailing assumption. You know, or is the test statistic in this case is higher than the critical value, then we would do likewise. Now, normally when we're doing these things, what we kind of can easily get our hands on is the alpha level, because that's what we define as our significance level, and the test statistic, because that's what comes out of our data observations. So we've got two choices. We can either convert our test statistic to a p-value. Again, we're just taking a value and looking it up in the normal distribution table or on the calculator that corresponds to these parameters. Or we could take our alpha level and turn this into a value. So we'd have to do sort of an inverse normal using our calculator. And then we've got, you know, so we can either compare those or compare those. We could do both, but not much point in doing that, to be honest. Okay, so that is the general idea, really. Just one thing, this doesn't really relate to the hypothesis test in general, but just something that if you are actually doing these kind of problems and you know, it might just be useful to note this, that here we go, I'll just read it. The points at which the curve changes from being concave up to concave down are called the inflection points. So if you can imagine this bit of the curve here, the center, the sort of rotated around some point here. And this point actually moves because you can see the curvature changes. Here, it's on the inside. So it goes from the outside to the inside. And so at some point along this graph, it changes from the outside to the inside. And graphically, we can see that it's there. And that actually is one standard deviation if we're talking about the normal distribution curve, which is quite interesting. You can prove that if your calculus is really up to scratch, you could probably do that yourself. I'm sure you probably could. Anyway, so yeah, these inflection points are always exactly one standard deviation away from the mean. So just something worth knowing about, and could affect, you know, when you're actually drawing these things, and just to make it look kind of more realistic, really. Okay, now the other thing we need to know about is the difference between one-tailed tests and two-tailed tests, because sometimes in our significance tests, what we're interested in doing is saying, well, we take a hypothesis that the mu is this some baseline value, and the hypothesis is that, well, actually the mean is something bigger. It's greater. And in other circumstances, a little bit, then what we might be doing is just proving that that is not the mean. I mean, this is before we've taken any data, remember. So it may be, you know, this might be a situation where we've we've improved things, and we've got some process, and we're trying to show that we've improved productivity of an industrial process or something like that. So that's what we're trying to do. But this applies to different circumstances where we might just want to, establish whether or not some assumption about the mean is reasonable or not. So anyway, that will kind of come out in the examples. So if we talk about a 5% significance test, then that 5% is all at one end. And here it's a greater than, so we're actually looking at the right-hand ending. If it was less than, we'd be looking at the left-hand end. Here, it's still a 5% significance test, but we split that 5% between the two ends. Okay, so that's the difference. Okay, so let's just move on. Have a look at an example. Right, an automobile company is looking for fuel additives that might increase gas mileage or petrol mileage. Without additives, their cars are known to average 25 miles per gallon with a standard deviation of 2.4 on a road trip from London to Edinburgh. The company now asks whether a particular new additive increases this value. In a study, 30 cars are sent on a road trip from London to Edinburgh. Suppose it turns out that the 30 cars averaged 25.5 miles per gallon with the additive. Can we conclude from this result that the additive is effective? Yeah. Okay, so are we doing any good, or does it not make any difference? And should forget about it. Okay, so now one thing to note here is this X bar. If we go back to the sampling distribution video, we realize that actually this has been averaged over 30 cars, and note 30 because 30 is kind of a bit of a threshold, if you like, for when we can actually start to assume that it's normal distribution. And incidentally, it does not say here that with this average mean of 25 and the standard deviation of 2.4, that this is normally distributed. It could be any distribution, but this we are taking as being normally distributed. Okay. All right. So what do we do? First of all, we identify the population and the distribution. So the actual population from which each trip comes is this. It's got a standard deviation of 2.4. Hypotheses are, first of all, that the mean actually is 25. That's what we've established. We're sort of trying to disprove it. And therefore that the alternative hypothesis is that mu is greater than 25. So this is a situation where we're interested in a one-tail test, and it doesn't actually ask us in this what, or it doesn't tell us what significance level to use. Very often that's the case. Here we're actually making our own choice. So so we take 5%. 5% is a very typical value to take. If in the absence of any information or any instruction, then 5% is probably a good one to take. So the test statistic, we've got 25.5. That's what this is. And this is drawn from a distribution which is normal with a mean of 25. And this, of course, this is the variance of it. Okay, so so the probability that this is greater than 25.5. Okay, I'm not getting the calculator out on this occasion, but if we plug that into our calculator as we've done before with a menu 7 and then a cumulative normal distribution, we can enter these parameters. The standard deviation will obviously be 2.4 divided by the square root of 30, and we get this, and this is our p-value. So 0.127 is what what we've got. Now that is not, is not particularly low. If it was 0.0127, we would be saying, well, very unlikely that this figure here could have been obtained from with these assumptions. Okay, but on this occasion, this is quite high, and what we're just saying basically as well, it's just random variation. Okay, so so the p-value is greater than the alpha value, so we're going to accept H0, which basically means, stick with what we've got, essentially. Okay, so that is that one. And the majority of these normal distribution hypothesis tests will involve the sampling distribution. Right, another one. The height of sweet pea plants grown in a nursery is a random variable. A random sample of 50 plants is measured and found to have a mean height of 1.72 and variance of 0.0967 meters squared. Calculate an unbiased estimate for the population variance of the heights of sweet pea plants. Now, there's a little bit of a twist in this question because we're not actually told what, it doesn't say this is your underlying assumption of what the mean and the variance is. Just read part 2. Hence, test at the 10% significance level whether the mean height of sweet pea plants grown by the nursery is 1.8 meters. Right. Okay. So, to be honest, this is kind of where the hypothesis test does get a little bit tricky in the way that some of these questions are actually written. So the implication here is that, this is what we're testing against, this 1.8, mean of 1.8, fine. But we're not told what the variance or standard deviation is that goes with this null hypothesis. Now, we can get around that if we take a sample and use that sample to estimate the standard deviation of the variance. And that is exactly what this has done here. So we've taken a random sample of 50 plants and found that it's got so this is the 50 plants that's got this variance. Okay, we've measured the variance of these 50 and got this figure. Now, if we were to apply this to the whole population, then of course what we're doing is we're using the data that we've got from our sample to estimate the population. And if we go back to a previous video, we realize that actually, if we just take the variance of these 50, then that is a biased estimator. It basically underestimates the variance of the population. So that we have to apply our correction. Again, this is in a previous video, so you might need to go back and have a look at that. So in order to do that, what we need to do is we need to correct. So this is our n, and this is our n minus 1, if you can hark back to that particular thing. So we need to apply that correction to this biased estimate to give us an unbiased estimate. So this is our estimate of the variance of the population. Okay, so does that leave us? Right, so now we're in a position to make our hypotheses. So first of all, that the mean is 1.8. Secondly, that the mean is not 1.8. So this is going to be a two-tail test at 10%. So we're actually looking at 5% tails on either end of the normal distribution. Our sampling distribution is going to be, well, it should be an n there, but normal with a mean of 1.8 and a variance of 0.0987 here divided by 50. And that actually, if we kind of work that through into a standard deviation, that gives a standard deviation of 0.0444. So then what is the probability of getting a test statistic? This now becomes our test statistic of 1.72, given those parameters, and that turns out to be 0.0358. Now 0.0358 is basically we're testing that against well, half of 5%, because it's a two-tailed test. So we're testing that against 0.025. Well, it's greater than 0.025, so it's kind of falling more in the middle of the normal distribution. So therefore, we're basically saying, well, it's unlikely. It's basically bigger. It's a 10%. I beg your pardon. So 5%. So we're actually saying that 0.358 is less than that 5%. Sorry, 5% is less than half, and then it's half of 10%. We're doing a 10% significance level. Sorry about that. So yes, so 3.0358 is less than that. So therefore, it's unlikely that 1.8 is the mean. So we're going to reject H0. Now, we're not saying anything in here as to what the mean actually is. There are different processes that we might use in order to determine that. I mean, point is, of course, why 1.8? There may be no other data on this at all. The only data we've got is 1.72. So if that were the case, we might say, well, our best estimate now is 1.72. That's our best estimate of the mean of this of the population of sweet pea plants. So there's some other stats here that we're not really covering under this. We're just kind of doing the hypothesis test and deciding whether or not we go with the assumption stated in the question. Okay, so that is pretty well that. And something slightly not right about this question, if I have to say, is that we're actually using the variance from this same sample that we have taken the test statistic. And I think actually, if we put that in front of a panel of leading statisticians, I think they might shut that out. Nevertheless, that's what the question setters asked, so that's what we've done. Right, okay, so basically a couple of examples there. Hopefully that starts to come clear, and also hopefully it's kind of demystified it a little bit for you. And so I think most of the difficulties with these problems either come with using the normal distribution, or with the way that the question is phrased, which makes it not always obvious what your null hypothesis actually is. But that's just the way it is. So hopefully that has been useful, and we'll be covering more hypothesis testing with the binomial. So I will see you in the next video.